Assalamualaikum. My name is Muhammad Akin Nazmi bin Muhammad Nasir. Today I will be presenting our MEMS electrostatic actuator design and its principle of operation. The design principle involves the use of tri-electrode topology, which includes two underlying stationary electrodes compared to the conventional topology, resulting in a compact structure. Like perforated intermediate electrode controls the MEMS moving electrode, while the bottom primary electrode provide fixed background electric field and field to enhance the attractive electrostatic force and compensate for the smaller effective area of intermediate electrode. This configuration allows the perforated intermediate electrode to enable similar deflection as the conventional topology, but with a lower controlling voltage. The tri-electrode topology also provides a longer displacement before snap-down occurs, larger than the 1/3 of the initial gap of the conventional actuator situation. Overall, the upper part of the actuator operates based on the principle of electrostatic force modulation and background electrostatic field enhancement to achieve lower controlling voltage and extended controllable range. So we design only the upper part.
In smart agriculture, the electrostatic actuator design can be used to control and manipulate agricultural equipment such as valves, pumps, and sensors. The low controlling voltage and extended controllable range demonstrated in the tri-electrode actuator can be used to development of agricultural machinery and systems. The compact size suitable for agricultural sensors. Thank you.
Hi, my name is Muhammad Azim Akram bin Abdul Halim. I'll be explaining about the fabrication simulation in the MEMS Pro software. So this is the layout we use in MEMS Pro software. We have the part by part layout, and next to it we have the assembled part. And then we have the layouts parameter. Each layout comes with various shape, which is box, frame, and customized shape. All the layouts have their own width and height. Next, we will move on to the material database. For the material database, we have silicon and aluminium. Actually, we have oxide layer material database, but because in the MEMS Pro simulation, we didn't include the oxide layer sacrificial layer, so we didn't include the material database for it. Moving on, we have the process definition, which only have 4 steps. The first is wafer, second deposit aluminium, third is etch bottom silicon, and lastly etch silicon and aluminium. The simulator result and top view in the article should be the same. That's all.
Hello sir, I am Kavin Raj. Now I am going to explain about the result that obtained when simulate the membrane with different thickness. While comparing the force and displacement of each table, as the force increase, the displacement also increase. As the membrane is more thicker, the displacement rate is higher than the original thin membrane. This applies to the voltage. As more thicker membrane required, more voltage for displacement. Thank you.
Okay, the objective is to observe the effect of center pieces length on the simulation result. The input and output of the simulation should be the same as the previous or the original, which are the input is voltage and the output is displacement. This is our result. Based on the result, we can conclude that if we increase the length of the center piece, it will cause the input voltage needed to use in order to move the displacement have to be increased as well. Uh, that's all for the NC simulation if we change the parameter of the lab.
For the part parameter, my part is geometry, and the objective is explore how changing the shape from a rectangle to a hexagon affect the design in terms of strength, efficiency, and functionality. We want to understand how this shift influence things like how material are used, where stress is distributed, and overall performance. When we change the shape, it's not just about altering the overall area. It also lead to noticeable boost in both displacement and force. This means the specific shape choice has a big say in how much the structure can move and how much force it can exert. So when we switch from one shape to another, it really impact not only how much space it cover, but also how much it can move and push. This show that the shape is a key player in determining how the system behave and perform.
For my parameter is to change the materials. So for the MEMS electrostatic actuator, the parameter that my part that I change is materials. So there's difference that happen when I'm changed from aluminium to zinc. From what my observation is that I saw that the force that were needed for the zinc to bend is much more lower than the aluminium. So this will make the voltage displacement that were needed for the zinc is much more lower than the aluminium.
Assalamualaikum, my name is Muhammad Afiq Firdaus bin Muhammad Azmi. For the SDG, the experimental analysis of low controlling voltage tri-electrode MEMS electrostatic actuator for array application aligns with sustainable development goal, particularly in advancing energy efficient technology and fostering innovation in industry, infrastructure, and smart city application. The research contribute to affordable and clean energy solution and environmental consideration by assessing the impact of low power technology, emphasizing responsible consumption and sustainable manufacturing process. Fostering partnership between research institution, industry, and government promote collaborative effort for knowledge sharing and resource utilization. In summary, the study highlight the significance of advancing technology in line with global sustainability goal, emphasizing innovation, energy efficiency, and responsible production and consumption.